Alright, so we're going to talk about functions a little bit. Before we get into anything, I want to go back real quick and talk about domains and ranges and how we gain that information from a graph. We've talked about how we do it analytically by hand, and we'll continue to work on that throughout the year. But I want to talk about how we pick a domain and range out from a graph. Remembering the technique, I think, will help people that usually put these things backwards. For some reason, throughout every year that I teach this, the number one issue is that people put the domain and range backwards in regards to the intervals. Not necessarily saying the domain is the range or the range is the domain. But for some reason, the number lines are backwards. When we look at domain and range, simply what we're doing graphically, and we do it by hand as well, it means the exact same thing by hand, but we're trying to find the infinite number of ordered pairs that are maybe on that blue curve. Okay? And if I were to be able to write out all those infinite ordered pairs and list them, okay, and then take out of those ordered pairs all the x coordinates and put all the x coordinates in a group, that would be my domain. And then take out all the y values or all the f of x values and put them in a group, that would be my range, right? Okay? There's an infinite number of values, so that's kind of impossible to do. So we developed the notation of interval notation to help us do that. When we look at domain, what I want you guys to understand is looking at domain, maybe one of the best ways of doing it is to take a kind of an imaginary line and just start drawing that imaginary, running that through your graph from left to right. And once that imaginary line starts intersecting your curve, there's your first domain value. Does that make sense? Okay. That's where you start, so -3, and I keep getting domain values as I pass through, right? Okay, so that little orange dot up there, where my cursor is an ordered pair, and its x value is going to be that x value right there. Okay, and it would be part of that list of infinite x values that are on this curve. And we keep going, until we get to a break, or we get to the final x value that our graph has. So our domain in this case would be that interval. And it looks like it's going from like -3 to 3.5, right? So we'd write that interval for our domain. And it's all dependent, obviously the graph will be a little bit more explicit when we see it in WebAssign or our textbook or whatever. Whether that'll be a closed dot or an open dot, let's just make them closed right now. So then that would tell us that we have a domain that goes from -3 up to maybe 3.5, and we'll include both those. Does that make sense? Okay. So that's my domain. The range is the one that people struggle with. Okay. The range, we're going to do the same thing, but now it's going to be a horizontal line. Okay. And the domain, you always look left to right. You always read a graph left to right. And we're going to understand that at the same time we're reading it left to right, we're trying to read it from bottom up too. Okay, so the range is going to be a horizontal line that we go intersect. Down there looks like a negative, like 1.8 maybe. And I keep moving that horizontal line through my graph. And we recognize that those are y values. See, these green values are the respective y values off of that graph, right? And I keep going, and now here's a certain situation. This did not happen with that vertical line, right? That vertical line only ever intersected one time, okay? Because it was a function. But we can have a horizontal line intersect multiple times. But they still all have, that point there, point D, point E, and maybe whatever this point over here we call. Do they still all have the same y value of like -0.5? Yeah, okay? So we just record it, and we'd have like a coordinate of like -2.5 comma -1 or -0.5. Here we have maybe like 1.75 comma -0.5. And here we have maybe 2.5 comma -0.5. 3 different points, but we still have a y value of -0.5, and that would become part of that infinite list of f of x values, right? Shows up 3 times, but as long as it shows up once, it gets included. Okay? And we keep drawing that line through, keep raising it through the graph. Eventually, at some spot, okay, you're going to see that after we move this line a little bit further, that intersection is going to disappear, right? but I'm still going to have two intersections over here. Okay? So I'm still going to have y values that go above 1. And that looks like that's going to be my last set of values that intersect. So we're seeing that our range then maybe went from negative 1.8 up to, let's say that's comma 1.8, I don't know. And let's say we include those values. So those would be my range values. Read it from the bottom up. Does that make sense? I get a lot of people want to read this from top down. I think that might be human nature to just want to go top down. It's how you read a book, right? Left to right and then top down, right? But with a graph, we're going to read from the bottom up. Because when we write our interval notation, this has to mimic a number line, right? And they have to be in chronological order then, so this has to be the first number in comparison to that one that we would see on a number line. Okay? What happens though, and we're going to see this a little bit today and tomorrow, is that we don't always have to have a really nice, we call this a continuous graph. And what I mean by that is if you were to put your pencil on this graph, right there, could you trace the whole thing without lifting your pencil? Okay? So that's what we mean by continuous. Okay? This graph, would you be able to do that? No, right here you've got a gap. You've got to jump over here. You've got to lift your pencil off the paper to come up here. This would be considered a discontinuous graph, okay, or non-continuous. But we look at this domain, and it looks like we're starting at negative 3, right? Those are the x values. Highlighting those x values on the x-axis for us. And it looks like we get a domain that goes from negative 3 to 0. Let's say we're going to include those things. So negative 3 to 0. Okay? But then I get back to moving. Now that vertical line, that orange line, is not intersecting any values, right? So those x values are not part of my domain because they're not intersecting my curve. Okay? It doesn't happen until about, what looks like about 1.5 again, that we start intersecting our curve. I don't like keeps doing that. Start moving that through, and it looks then like maybe 3.5 would be the last x value. So we have another list of values that started at 1.5 and went to 3.5. And what we're saying is that all of these x values here have to be part of my domain. And all of these x values have to be part of my domain, right? So domain comes from these, or domain comes from here. So we have to union those. We have to stick those together. Is that all right, everybody? Okay. And that's how we would refer to that domain graphically. The range, again, starting from the bottom and moving our way up. Okay. There we start getting 2 points that have the same y value, but that's fine. Okay. Now here, we notice that we're going to stop. Eventually, we're going to stop intersecting this portion of the curve. But I maintain intersecting over here, right? Okay. So from negative maybe 1.5 all the way up to right now 2.5, I've incorporated all those y values. Okay. Whether they came from over here or they come from over here, there's not a single y value that we're missing in between negative 1.5 to right now maybe 2.5. And I keep moving that through. It looks like it goes up to about 3.5. So every single y value from negative 1.5 to 3.5 was incorporated either from this curve or from that curve or from both, right? Okay. And that's how we want to be able to write our range values. Okay, here's a third function. It kind of incorporates everything that we've talked about so far. We got a domain there that would be a union, right? Okay, we had negative 3 up to 0.5, and then 1 up to 3.5. And if I look at the range kind of has a similar behavior. We skipped some values in there, right? Okay, we would not record those y values if I was listing all the ordered pairs from this graph. But then we start at like a y value, I don't know, maybe 2.7 or something like that. And then continue that through up until about maybe 4.1, 4.2. Okay? So we would eliminate or remove these points here. Okay, on a range, we would say maybe goes from like negative 1.8 up to maybe 1.9. And then we union that with, I don't know, 2.6 to 4.1. And again, I'm just ballparking kind of those points that are on the y-axis. But it has to be a union. Is that okay with everyone? Okay. This type of graph and this type of graph, F2 and F3 in this applet, are referred to what we call as piecewise functions. Okay. Because they're pieces of graphs. Does that make sense? And we'll talk about piecewise functions maybe a little bit today, depending on how fast we get through some of the other stuff. That's part of this section. Another thing I want to talk about, we started getting into this yesterday. I think we stopped maybe here when we start talking about power functions. One thing I want to make sure we all understand before we get to power functions, let's talk about constant functions first. If I have just a simple graph, y equals some constant, I'll just call that constant c right now, okay? If I have some constant c, y equals that, okay? It becomes a horizontal line through that c value. Does that make sense? Okay, so here we're seeing y is 1, but as I move c, it could change to 2 and 2, whatever. There's to 2, okay? And now it's a horizontal line through 2, right? And the reason for that, hopefully we recognize and remember this from Algebra 1, okay? However many points I have on there, and how many I highlight, if I look at their y values, what are their y values always going to be? 2. No matter where these points go, it's constantly 2, right? Oh, B came off the line. Okay, they're always 2, okay? And another word for always is constant. Okay, so that's what we call a constant function. Does that make sense? Okay. So y equals 2 is a horizontal line. The way I remember it is when you see something like this, y equals 2, the letter they're using, the variable they're using tells you what axes you're crossing through, and the 2 tells you at what number. Okay? Because we can change that and say x equals some constant. Let me get rid of these points. Okay? Is the music playing now? Alright, so if I look at those ordered pairs, now we got x equals, let's just go over to negative 1.8. What do you notice is constant over here now? The x coordinate, right? And it's telling you again, x is the axis that your vertical line is passing through, and it's doing it at that number. Okay? It's one of those situations, I think constant functions are an extremely easy concept, and it's so easy, we overcomplicate it. Does that make sense? Okay? There's a lot of things in math that we do that with, so I want to make sure we don't overcomplicate. I'll give you, I was looking at the test that they have provided us for this course, and there's a question on there that asks you interpret y equals 2 or graph x equals 3 or something like that. Okay? Should be easy points, but a lot of times we miss those. I get maybe a third of the class every year to miss stuff like that. So make sure we understand those constant functions. Constant functions are kind of give you an idea here. They're kind of what we call if I just say like x equals 0, okay, or x equals just c or something like that. We call that a parent function, okay? And a parent function is kind of maybe the most basic or most simplistic type of function you can get, okay? And as I start changing that value of c, we start to get kind of like the children of that parent function. Does that make sense? Graphs that are different, but very similar to the parent. Does that make sense? Like you guys are children of your parents, right? You're different than them, but you probably have a lot of similar characteristics, right? Okay. And then we put all these things together, all these graphs together, and we get what we call a family of graphs. Families should be sharing similar characteristics. Okay. The ones that maybe you've seen the most, you've dealt with the most, is something like y equals, or f of x equals a times x plus b. And let's say that x is 1. Let me change it real quick. Okay, so the one that you're maybe most familiar with, the most simplistic parent function that we can have for a line is y equals x. That's what we got right here, right? Okay. But we can start chaining, we can add numbers to it, or we can multiply it by some real number, some constant, okay, some multiple, and we get then what looks like new graphs, right? But are all those graphs kind of similar to the one we started with? Okay, they have similar relationships. And we can move that graph up and down, right? So this graph here is, or what we know about that graph can be learned through understanding what y equals x looks like. Okay? If I know what y equals x is and some features of y equals x, then I have some understanding of y equals 4x plus 8. Okay? Maybe another one is something like f of x equals, we'll just use a times x squared plus b times x plus c. Okay? That's going to be our parabola, right? Okay? And again, the one that you're most familiar with, change these. Wish it would default it to integer values for me automatically, but it doesn't. Change it to 0.5. So the one you're most familiar with, what we call the parent function for quadratics, is when c is 0 and when b is 0, and you get just simply x squared, right? Okay. But we know that we can move that thing around, change what it looks like, okay, and we get other parabolas, right? Well, that parabola, the information that we know about that parabola, can be gained for what we know about A1, what we know about that parabola, okay? So if you know something about the parent, you should be able to know something about the family of graphs. Does that make sense? Okay, and that's kind of what a lot of this course is going to involve here in the near future. Couple of the types of graphs that we're going to deal with right now are called power functions. Okay, so if I have f of x equals x raised to some power, we're going to call that power n. Okay, let me change the font size so those of you in the back might be able to see this stuff a little better. Okay, a little ridiculous, but we see f of x equals x if I have a power function. Now I want to change this to, so I'm not really worried about power functions that are non-integer. Okay, so I want to keep my n value to be a 1. So the first kind of power function we can better interpret as linear. Does that make sense? Called a linear function. But when I have x squared, it is a power function. X to the third is a power function. X to the fourth is a power function. Okay? But hopefully you start to recognize as I scroll through there, don't they kind of alternate back and forth from one to the next and then back to the other one? Okay? What I want you to realize though, I'm just going to deal with the quadratic real quick. Let's go start at 0 here. We'll go to 12, and we'll go by increments of 2. So I'm just forcing my exponent here to be able to start at 2, and then go to 4, and then go to 6, and so forth. If I start at 2, that's my parabola. If I get x to the 4th, it looks like that. Okay. Now it's a little bit stretched, right? Okay. Think about what's happening here. If I highlight a point on this curve, let's go 2, 4 right there, right? When I go to make this thing x to the 4th power, it's going to take that x value of 2 and raise it to the 4th power. It should go to 16, right? So an x value of 2 on the parabola is a much smaller y value than it is on there. Okay? And then when I go x to the 6th, now I'm going to take 2 and raise it to the 6th power, and it gets up to 64. And then 2 to the 8th power, it's all the way up to 256, right? So the y values are getting much bigger, much faster, the higher the exponent becomes. But all these things are very similar. Does that kind of make sense? X squared, x to the 4th, x to the 6th. I don't ever want to deal with x to the 100th power, but hopefully if you know what x squared looks like, you know x to the 4th looks like, x to the 100th power is going to be very similar looking. Does that make sense? Okay. And what happens though, maybe looking at it this way, numbers that are bigger, numbers that were bigger than 1, we're getting a lot larger after I square them, or raise them to the 4th power, raise them to the 6th power. When I have a number like, let's say, let's see if I can get 1/2 on here. Let me scroll in. Okay, so close to 1/2. If I take 1/2 and I square it, you get 1/4, right? And that's what that's saying right there. But when I take 1/2 and I raise it to the 4th power, okay, now I'm getting 1/16. Well, that's 1/16 right there, okay, or something very close to 1/16. And that's why this y value got smaller, right? So numbers between 0 and 1, as the powers get larger, you start to see that those values start getting closer and closer to 0, don't they? So the larger the exponent, okay, after 1, the y values are getting very, very large. They're getting closer and closer to infinity. Between 0 and 1, your y values are getting closer and closer to 0. It's because that denominator is becoming a much larger number when I raise it to the 4th power, the 6th power, the 8th power. Okay? So that's kind of the features that we recognize. So what's nice about that is if we know stuff about those two things, okay, then we know stuff about these things. Okay? So analyzing some very simple looking curves can help you understand some more complex curves. Alright? So now let me change this to start at 1. Okay, so if n starts at 1 and increases by 2's, now we're going to get odd powers, right? X to the 3rd is going to look something like that. X to the 5th is going to look something like that. X to the 7th, something like that. X to the 9th, okay? They all look kind of similar, right? Okay? So whenever you are told or discussing things called parent functions, you might get a chart that looks something like this. Now, it's not a complete chart because they're only showing you here what we call our quadratic and our cubic functions, right? But if I know my quadratic, x squared, inside that and an understanding of that is that you should also know x to the 4th, x to the 6th, x to the 8th, basically x to the n when n is even. Okay? And then you should know, same thing, x to the n when n is odd. Okay? And they're going to show those similar behaviors. Something that we're going to want to do for a lot of these functions is to recognize and learn and be able to recall just a couple key ordered pairs for every one of them. Okay? And eventually we're going to use them so much that they just become second nature. So we're not really memorizing, we just know them. Okay? Hopefully you already know from maybe Algebra 1. Maybe those are kind of the best grouping of ordered pairs for us to know, or x-coordinates for us to know, for the parent function x squared. Because if I know those, you should know the y values to go with them, right? And that's going to be enough for you to graph and get what looks like almost a comprehensive graph, right? The fear is, okay, that I have is that when we start trying to graph a lot of functions is that maybe we only choose those ordered pairs, those x values. If I just chose those x values, the graph that I would get would just be that portion of the parabola, right? Okay? It's not a comprehensive graph. It's not the full thing. So we want to make sure that we understand a handful or a cluster of points for all these functions that will develop initially an entire graph or an idea of the entire graph that we can kind of manipulate and work with. What is also nice about this is that eventually we're going to be asked, okay, what does f of x equals 3x squared look like? Well, if I know what the points of x squared look like, 3x squared, what this is saying is that your y values are 3 times what they were for x squared. Does that make sense? So here, if I know my x and y's from this graph, -2, -1, 0, 1, and 2, this is saying your y values are 3 times as big. So 12, 3, 0, 3, 12. And I can graph this pretty quickly, knowing what I knew from this one. That make sense? Being able to multiply. Even if I subtract, now maybe I subtract 2. Well, now that means my y values are 3 times this, remove 2. So now I have 10, 1, -2, 1, and then 10. And I can graph those pretty quickly and get what 3x squared minus 2 looks like. Okay? Ultimately, that is a use and a need that we have to graph things, but eventually we'll also learn some other techniques that allow us to graph it much quicker than that. Things of like, and we'll do a couple of these, but like f of x equals x cubed. Okay, so again, some key points are -2, -1, 0, 1, and 2. But if I cube -2, I get -8, right? If I cube -1, I get -1. Cube 0, I get 0. 1 and 1, 2 gives me 8. And now I have that cluster of points in my mind that I'm going to use. It kind of doesn't make a whole lot of sense to go to 3 and 4. So I cube 3, I get 27, right? I start getting things outside of the range of values that I really want to graph. That's a really big number to graph. And then usually the idea is if you understand these two concepts, you should be able to do x to the 4th. You should be able to do x to the 6th. But a lot of times they don't ask us to do that because think about like just x to the 4th right away. Okay, if I just start choosing -2, well, it already gets me -2 times -2 times -2 times -2 already gets me to 16, right? Well, that's kind of, if you had a graph, that's kind of a pain in the butt to graph 16. If I went x to the 5th, -2, an x value of -2 already gets me all the way up to 32. I don't want to have to graph that, right? Okay? So they focus a lot of their attention on x squared and x cubed, and then hopefully we can build a bridge, build relationships from those things to learn about x to the 4th, x to the 5th, x to the 6th, that kind of stuff. Same thing happens with root functions. Okay? Root functions, let's say I have f of x is equal to the square root of x. Okay? Which we also know that to be written as x to the 1/2. Okay? Those say the exact same thing. When we graph those, we got to think about our domains because there are some values for x that we cannot take square roots of, right? What values can we not take square roots of? Negative numbers. Okay, so when I look at my function, maybe f of x equals, I'm just going to rewrite it as x to the 1 divided by n. Okay? Create a slider for n, change it from 1 to 12, and we'll increase by increments of 1. So again, it's kind of trivial when your n is 1, so you got x to the 1, which is just the linear function, right? But when n becomes 2, you get x to the 1/2, or the square root of x. Okay? And you see then that that is your set of ordered pairs, right? So a key set of ordered pairs for this graph are 1, 1, and then 4, 2 are useful. And if you want to go far enough, 9-3 would be a useful group.